Can you see the whiteboard?
Yes, ma'am.
And let us learn skew symmetric first. Then we'll learn Hermitian, and then one by one another all. Okay.
Okay. Are you writing anything?
Yeah.
I'm not able to see it, ma'am.
Okay. Okay. Let me write it again. So you know semantic matrix already.
Yes.
So I'm just writing about skew semantic matrix.
Okay.
Okay. Okay. Let me. So I'm just now tell me if you can see. I'm just resharing you. Mm, can you see now?
Yes, ma'am.
Symmetric matrix, you know very well. In
The transpose and the original matrix are the
yes,
same.
yes. Now let us learn skew symmetric matrix. When we have like A transpose is equal to minus A.
Okay.
Okay. And also we have all elements of diagonal 0. Okay.
Okay.
And all Aij are 0 when I
I
is
equal
equal to j. Yes. Okay. So let us take few example. We are taking example if we this matrix P having element 3 and minus 3 and having another 0. Similarly, we can take example of this of 3 by 3. We are taking all diagonals elements 0 and take minus 1, 5 and 1, 5, 2 and minus 2. Okay. Now these are examples of skew symmetric matrix. So you got it?
yes, ma'am.
If you got it, shall I explain you again?
Got it, got it.
Okay. Now let us understand the Hermitian matrix.
Omission is that conjugate concept, right, ma'am?
Yes, exactly. So you know that?
I read it. I just didn't. I don't know if I know it correctly. So.
Okay, okay. Sure. Can you see the whiteboard?
Yes, ma'am.
Okay. Hermitian matrix is just what that is equal to its conjugate transpose. Hermitian matrix. A Hermitian matrix is a matrix that is equal to its conjugate transpose. We can understand by using an example like we have matrix A having 5 minus 3 and 1 minus iota and 1 plus iota. So we can find its transpose. 5 iota, 1 plus iota and 1 minus iota, 1 minus 3. So here we can see that we have this equal sorry matrix A is equal to its conjugate transpose, because we have here conjugates of 1 plus iota, we have its conjugate 1 minus iota. Similarly we have 1 minus iota and its conjugate, here we have 1 plus iota. So are you getting
Okay.
these? You got it, or shall I explain you again?
Can you tell
You
me
got
how
it?
to find conjugate for a number?
Pardon?
Can you tell me how to find conjugate for a number, ma'am?
Okay, okay, all right. See, we have complex number because we find conjugate obviously for complex number. So we have complex number like z is equal to a plus iota b. Then its conjugate is denoted by z bar, and just we take opposite sign of iota. Okay,
Okay.
conjugate of z is z bar, and that is equal to a minus iota b. Or do you remember this iota?
Yes,
That is
root of
equal to
minus.
square root. Yes, exactly. Okay.
And for real numbers, a Hermitian matrix would be its transpose itself.
Yeah. Yeah. Conjugate transpose. Okay.
But for real numbers, there's no conjugate, right, ma'am? So,
But Hermitian matrix is about only for complex number. Okay.
okay.
Yeah. Because
Because it,
for real numbers we have symmetric and skew symmetrics, and for complex we have Hermitian and skew Hermitian. Okay.
okay. But
Yeah.
then, in that question, the Frobenius inner product, over there they've told it's a real vector space and not a complex vector space. So, if A
So
of H is a Hermitian transpose of A and it's in a real vector space, then that means it doesn't have any complex components, which means it's
yeah,
just it's
you can consider this imaginary part as a zero in this case. Okay,
okay.
we are just taking like this b is equal to zero in that case. Okay,
Okay.
yeah,
B is equal to 0. Got it.
yeah. Now let us know about skew Hermitian or Hermitian skew matrix. Okay, shall we?
Okay. Yes.
Uh, because in that case which we have the question, they'll make us confuse because as we know we are doing for that definition for real numbers, and
Mm.
Hermitian matrix is just about a complex number, so they make us confuse, and we need to just check it what we should do for that. Okay, that is why. You got it?
Okay, ma'am.
Yeah. Similarly, we have here means for skew, just we take a negative sign of that. Means similarly as of skew symmetric matrix, here in symmetric matrix we have transpose is equal to matrix itself, and for a skew we are taking to its negative, right?
To the negative sign of the
Similarly,
con.
yes, similarly with Hermitian. Okay, here we are taking conjugate and matrix means they are equal. Means this is equal to its conjugate transpose. Okay, but in skew we'll take its negative along
Okay.
with negative sign. Okay,
Okay.
yeah. So skew Hermitian matrix, a square matrix A is said to be a skew Hermitian matrix if and only if A H is equal to, I'm telling you what is it, okay? I'm telling you,
Okay.
is equal to negative of A. And where this A H is conjugate transpose of A. Okay?
Okay.
This A H is denoted by conjugate transpose of A. If negative means negative of matrix is equal to its conjugate transpose, then we say given matrix is a skew Hermitian matrix. Okay. So now let us take one example to understand this well. You got this definition? You got? Or shall I explain you again?
Got it, ma'am.
Okay. So let us take one example. Or that is A, let A is equal to 2 iota 5 plus iota and minus 5 plus iota and minus iota. We have this matrix. We need to check if it is skew Hermitian matrix or not. So let us find first transpose. You know very well how to find transpose. Now let us find this AH. Okay. Conjugate transpose. Okay. So conjugate transpose of A we can find as AH is equal to, just put negative sign. Okay. Means take opposite sign of iota everywhere. So let us take, we have minus 2 iota. We have iota only because we have already minus, okay? Negative of negative. And minus 5 minus iota and 5 minus iota. Okay. So let us check if this equal to negative of A or not. Let us check it. So now let us take the minus common. And now we have 2 iota and here 5 plus iota, and here we have minus 5 plus iota and minus iota, and which is equal to, okay, white food is not allowed here, let me write here, minus 5 plus iota and here minus iota, so which is equal to minus A. So given matrix is skew Hermitian matrix. You got it?
Okay.
Do you want to ask anything or shall we do the next topic?
Let's continue, ma'am.
Okay. Now let us do orthogonal matrix. Orthogonal matrix. Let A or sorry A be any square matrix, then A is said to be orthogonal matrix if A into A transpose is equal to identity matrix, or you can say A is equal to sorry, A transpose is equal to A inverse. Okay, then we can say this given matrix is said to be orthogonal matrix.
Got it.
Got it? Yeah.
Ma'am, for these definitions and all, if you dictate it, I'll write it down because since you also have class right after this, I don't want to waste your
Yeah,
time in
yeah.
writing.
Okay, okay. Sure. So it would be better that I'll give you in the form of notes first, then I'll explain you. It would be better for you. Today I'll send
Like,
you in the
okay,
form of notes. Okay?
okay,
And then tomorrow I'll explain you. So let's do the next topic all of these. Is it
okay.
fine for you?
Understood, ma'am. Okay.
Okay. So let me check what is the next topic you have. Mm, just
Idempotent and stuff.
which one?
Some idempotent.
Okay, okay, idempotent. Okay. Idempotent matrix means when we multiply a matrix to itself, then it will become the matrix itself. Then we can say given matrix is idempotent matrix. You got
Multiply
it?
a matrix to itself.
Pardon?
When you multiply a matrix to itself, you get the original
Yes,
matrix.
yes, yes. Then we can say given matrix is idempotent matrix.
Okay.
Yeah. And next is nilpotent matrix. When we multiply a matrix itself, then we'll get uh, null matrix as a result. Then given matrix is said to be nilpotent matrix. For idempotent matrix, like if we multiply A, then we'll get, this is for idempotent. And for nilpotent, if we multiply A itself, we'll get this null matrix. And we can multiply as many as time, then still we'll get I identity matrix. Okay, and for nilpotent, when we multiply A itself any number of times, then we'll get again and again as a null matrix, and it is set to be nilpotent matrix.
Okay.
Got it?
Yes, ma'am.
Okay,
What's a projection matrix, ma'am?
sure, I'm telling you, just a second. Give me a few seconds.
Okay.
Do you have in your material, or shall I explain you with my? I'm just opening with the example also, so that we can do an example related to this.
Okay, ma'am.
So do you have your own material which you have sent me?
It's there, yes, ma'am.
Okay, okay, I'm just opening yours. Okay, I'm seeing in matrix PDF. Can you tell me the page number? If you can, I'm just opening this. Okay, unitary matrix, positive. Okay. You don't have here projection matrices. Let me check. Okay, in first one, I'm just checking next
I've sent it to you, ma'am.
one. Yeah. You send me just?
Yes, ma'am.
Okay.
1 minute, ma'am. I'll
Yeah,
come back.
sure. So I'm using my own material because here this is not well defined in this
Okay.
PDF. So give me a 1 minute. I'm just opening my material. Hello.
Yes, ma'am.
Hello. Yeah, I'm saying that it is taking some time to open. Shall we do some another topic right now, which we have in our syllabus? I'll explain you
Uh,
by tomorrow, okay? With real example, okay?
okay. Linear transformation.
Sure, sure, sure.
Ma'am, can you just explain to me like the assignment problem, like as opposed to doing topics? Can you help me
Yeah.
understand the assignment question?
Tomorrow I'll give you by finishing all of them. Then I'll explain you with condition and all formulas, okay?
Okay.
Is it okay with you? Because tomorrow when I'll give you before your class time, then I'll explain you in class, okay? Each and every question to you.
Are you able to see what I solved, ma'am?
Pardon?
I sent you one third problem. I tried to do it and I sent it to you.
I'm not able to open this. Can you send me in the form of PDF, please?
Which
Because
one,
I
ma'am?
cannot. Yeah, which you sent me today, third one. Because you sent me, I think, another in docs form. I'm not able to open this. So can you send this in PDF?
Okay.
Okay, later the class you can send me. Okay. Yeah. So let us understand now. Let us learn the linear transformation.
Okay.
Okay. So shall I explain you on your PDF or on whiteboard? What do you say?
Whiteboard, ma'am.
Okay, all right. Sure. So I'm using your material. Let V and W, or they are using V vector spaces defined over a common scalar field F in univariate vector space mapping. This mapping L from V to W is linear transformation if for all V1, V2 belongs to V, and for all S belongs to F. And we can define this linear transformation. We are taking when the, I mean, linear transformation of V1 plus V2, that is equal to linear transformation of means V1 plus linear transformation of V2. Okay. And also like L S into V1 is equal to S into V1. Okay, so this is the definition I'm telling you on whiteboard also.
Okay.
Yeah, and then we'll do example related to that.
Okay.
Linear transformation. It is a mapping. Okay, let V and W are vector spaces. Then mapping L is linear transformation from V to W is said to be linear transformation if L U V1 plus V2 is equal to L V1 plus L V2. What it means, I'll explain you by using an example, okay?
Okay.
And then if we multiply scalar S with V1 gives that scalar into L V1. Like the definition of vector space means these are two axioms to be satisfied. Okay, these are two axioms, like you can say two properties also, which we need to satisfy to show the linear transformation, okay, of the given vectors. Yeah. So here in your examples, you can see here 2.3.2. Okay, we have this matrix representation of linear transformation. We have L theta E1 to the power V, and which is equal to cos theta E1 to the power W. Okay, we have both. Okay,
Okay.
and yeah, we can represent them by taking like sum of two for left hand side. Okay, and then we need to represent in the form of like the split one with in this definition in this property which we need to show them. Okay. So shall I explain you in your PDF or here on whiteboard? What do you say?
On whiteboard.
Sure. I think this one. To do this example, we need to do one more topic in it. So I'm just giving you one another example of linear transformation, okay,
Okay.
of my own. Then we'll do the next topic and then we'll do this example 2.3.0. Okay.
Okay. Are you writing something on there?
Can you see that?
No, I can't see.
Just a second. Can you see now?
What are you writing, ma'am?
Example?
I can't see.
Okay, I'm just a second. I'm just resharing you. Just a second. Hello?
Hi, ma'am.
Hello?
Yeah, I can see your screen.
Can you see now?
Yes.
Just tell me clearly if you can see this. Okay.
Okay.
So suppose this example mapping from this R3 to R2.
Now I can't see, ma'am. I was
You
able to
can't see
see, and
this?
now and I can't see.
Just a second. Can you see now whiteboard?
Yes.
Hello?
Yes, ma'am.
Okay. So let us do example. Suppose mapping L to R3 to okay, to R2 is a linear transformation. With we have L having this form 1 and minus 1 and have 0 in the form of vector, and that is equal to 2 comma 1 means we are taking in this form, and result means output in this form we have.
Okay.
Okay. Similarly, we have next to L of 0, 1, minus 1, that is equal to minus 1 comma 3, and similarly we have L having this 1 sorry 0, 1 and 0, and we have output 0 comma 1. Now we need to find this is given, and we need to find CL or having minus 1, 1 and 2. Okay. Now let us find by using linear transformation. So how can we find it? Let us know. To find in solution, to find this L means linear transformation of minus 1, 1 and 2, we need to express uh, this vector. We are taking as a vector to this, okay, because this is vector uh, that we are taking this v is equal to minus 1, 1 and 2 as a linear combination of, let us take given these v1, v2, v3. Okay, let us take them as, so v1 we have 1 1 sorry minus 1 0, and v2 we have uh, 0 1 and minus 1 we have, and 1 because we have three vectors, so let us take this 0 1 and 0. Okay, and to form linear combination we need to assume alpha 1 alpha 2 alpha 3, as you know we need to take corresponding scalars also to form linear combination. Got it?
Okay.
So Let,
Can you write it on the side, ma'am?
pardon?
Can you write it on the side, please?
Okay, okay, sure. Let alpha 1, alpha 2, and alpha 3 scalars to form linear combination.
Ma'am, you don't have class at 7?
Yeah, I have. So, you want to leave or shall we complete this?
Is it possible for you?
Sure, sure. Okay. Let us finish in 5 to 7 minutes this question.
Okay.
I'm just messaging them that we are going to start in next 5 to 7 minutes. To form linear combination, now let us form the linear combination. And this, which we have to find, this one can be expressed as linear combination as V is equal to alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. Okay. So we have this like minus 1, 1 and 2 is equal to, let us take alpha 1 and write the vectors, or you can write this in this form also. In vector notation you can write as minus 1, 1 and 2. Okay, and take in vector notation like them 1 minus 1 0 and plus alpha 2, we have 0 and 1 minus 1 plus alpha 3, and we have next 0 1 and 0. So we can form here alpha 1 only and minus alpha 1 plus alpha 2 plus alpha 3 and minus, we have minus alpha 2 here, and just compare and find the values of these scalars. So alpha 1 is equal to minus 1 and alpha, sorry, 3 here. Okay, alpha 2, sorry, alpha 2, we have here 2, sorry, minus 2 because we have minus alpha 2, and alpha 1 is minus 1, and now we can put the minus alpha 1 plus alpha 2 plus alpha 3 is equal to 1. We can put now values of alpha 1, which is minus 1, and this is minus 2 and plus alpha 3 and is equal to 1.
Wow.
We can solve now for alpha 3. So we have minus 1 plus alpha 3 and is equal to 1. And we'll have here minus, sorry, alpha 3 is equal to 2.
Mm. Okay, ma'am.
So now we this linear combination can be expressed by using the values of these scalars. Let us use. So this linear combination means we can be expressed as we have alpha 1 is equal to minus 1, uh, that is equal to minus v1 plus 2 v2 plus 2 v3.
Would it
and
be minus
n
2 V2?
means
Negative 2 V2.
okay, okay, sure. Okay, yeah, yeah. Sorry, we have this negative, yeah. So now let us find a linear combination of this V. We'll express as linear combination of these all. It's minus V1 minus 2 V2 plus 2 V3. So we can split by using definition like this. Linear transformation of minus V1 plus 2 and linear transformation of V2 plus 2 linear transformation of this V3. So, we have this value of this.
Hmm.
We have here in question.
Yes.
In question, we can see we can put now values which we have in question, uh,
Oh yeah, yeah. 2 1 minus 1 3 1
yes,
0 1.
yes, exactly. We have here. So let us put now. So we are using here values, and so we are taking negative of that. So minus 2, 1 plus 2 times of minus 1, comma 3 and plus 2 to 0, comma 1. Now let us simplify. What will we have? Minus 2 and minus plus 2. Okay. So we are taking here, see, minus 2 and minus 1 we have here, plus 2. So we'll have here minus 2. Okay,
Ma'am,
let's
what
see.
would be
Yep.
uh,
Yes,
uh,
plus 2. Yep. Yes. We have
yeah.
minus 2 here. Yeah. We have minus 2. Sorry, not plus. Minus 2 here. And so we have here plus 2 and comma minus 3 and plus
6 9
here we have 0 and 2. So now let
2
us see.
minus 6.
Yes, minus 1 plus minus 3 and plus 2 we have.
Ma'am, minus 3 is actually
Oh
minus
yeah,
6,
yep,
right?
yep, yep. Sorry, I forgot here. Yep, minus 6, yes. So now let us add here minus 6. Okay, so finally we have 0, comma minus 5. Okay, so this is the required linear transformation for given vector. Now you got it?
Yes, ma'am.
In this way we can find. Okay,
Okay.
so we'll do further tomorrow, and first of all I'll explain you your assignment, okay, in class.
Yes, ma'am.
Okay.
Thank you.